Welcome back, AP Chemistry students, to Unit 6, Introduction to Thermochemistry. Today we will be talking about Unit 6.2, Calculating Enthalpy. Now I know you're thinking, Professor, we've already talked about how to calculate enthalpy. If I have a reaction, I can be given the enthalpy of that reaction as being positive or negative. If it's positive, then that means that heat or the energy itself can be viewed as part of the reactants. If it's negative, then heat is part of the products. And you can think of it as that heat for 1 mole of reaction, and therefore stoichiometrically I can determine the enthalpy change within a reaction. And that is true, and that is all very good information. However, there are multiple ways to calculate the enthalpy of a reaction besides just carrying it out and calculating the temperature change as long as pressure is constant. We can actually calculate enthalpy a number of different ways. So for every reactant and product, there is a standard enthalpy of formation. The change in enthalpy sub F shows the amount of energy necessary to form 1 mole of a particular substance from its elementary particles. So for example, if I wanted to form ammonia, that heat of formation is for the reaction to produce 1 mole of ammonia from elemental nitrogen and hydrogen. Now again, that heat of formation is the amount of energy needed to form 1 ammonia, and therefore the heat of formation reactions aren't always balanced with whole numbers. In the case of ammonia, it's half of an ammonia molecule and 1.5 moles of hydrogen gas to form the 1 single ammonia. Now these values are given to you in a table, and in order to determine the heat of a reaction from that table, we take the sum of all of the products' heat of formations, and we subtract the sum of all of the reactants' heat of formations, with any elemental substance having a standard heat of formation of 0, because we're not going to carry reactions out in the sun, so we're going to assume elemental substances are already formed. So we use the formula, the sum of all of the enthalpies of the products minus the sum of all of the enthalpies of the reactants will give us the change in enthalpy of a reaction. So let's try this in the reaction here. Aluminum and ammonium perchlorate produce aluminum oxide, aluminum chloride, nitric oxide, and water. We have our heat of formations for a lot of these substances, and all we're going to do is take the sum of our products and subtract the sum of our reactants in order to determine the heat or the enthalpy change for this reaction. So we simply use the table. We have 1 aluminum oxide with a heat of formation of a negative 1600 kilojoules for each mole. We'll add to that aluminum chloride, which is a negative 704 kilojoules for each mole. And we'll add to that nitric oxide, which is a positive 90 kilojoules for each mole. But there are 3 nitric oxides, so that heat of formation needs to be multiplied by 3 to be used correctly. For water, water's heat of formation is a negative 242 kilojoules for each mole, and again, stoichiometrically, there are 6 waters in this reaction. So, our products' heat of formation overall have a heat of formation of a negative 3,562 kilojoules for each mole. That is the heat of formation of our products. We're going to subtract from that the heat of formation of our reactants. So our reactants here, aluminum and ammonium perchlorate. Aluminum is elemental, so yes, while there are 3 aluminums, aluminum's heat of formation is nothing, because we are not a star. We are not going to be able to form aluminum from anything. So we are assuming that elemental substances are already formed, so their heat of formation is 0. So we're going to add to 0 the heat of formation for ammonium chloride, which is a negative 295 kilojoules for each mole, and again, there are 3 moles of them, so we have to take that into account. So the heat of formation of our reactants is a negative 885. So the enthalpy of the reaction is simply one minus the other, to give us a heat of reaction for this of a negative 2,677 kilojoules for each mole of reaction. Now, determining the heat of the reaction is just one way that this sometimes is posed to you on the AP test. The other way is to determine what's missing, meaning I'll give you all the players involved and you have to determine who's not there, right? So here you have how sugar is oxidized into carbon dioxide and water. This is what gives your body a lot of its energy by the release of that 2,800 kilojoules. So with that value in mind, determine the heat of formation for glucose, meaning we are missing a value here, right? If we looked at the equation above, we have carbon dioxide and water. Anything elemental is 0, so we have a value for that, but we do not have a value for the glucose. So we need to figure that out. We do have what the enthalpy of the reaction is. The enthalpy of the reaction is a negative 2,800 kilojoules for each mole of reaction, right? It's a negative because that energy is part of the products. Now, that value had to come from the sum of the enthalpy of the products minus the sum of the enthalpy of the reactants. So let's plug in the values we have and see if we can figure out where we're missing something. A negative 2,800 kilojoules has to equal 6 carbon dioxides, which were a negative 393.5 kilojoules for each mole, plus 6 waters, which were a negative 285.8 kilojoules for each mole. Now, whatever that value is, we subtracted our heat of the reactants. And our reactants are what we're missing. We're missing the glucose plus the 6 oxygens. But oxygen is 0. So really, all we're missing here is a value for that glucose. So we can determine what glucose is by simple algebra. So 6 times a negative 393.5 plus 6 times a negative 285.8 is a negative 4,000. Add 4,000 to both sides, and we get that the heat of formation for glucose is a negative 1,275.8 kilojoules for each mole. With that, you can practice this on page 15 of your packet. Another way that we can deduce or determine the enthalpy of a reaction is to look at the different mechanisms possible for that reaction to occur. In order for a reaction to occur, many different processes could happen, and if we take the sum of all of those processes' enthalpy, we can determine the change in enthalpy for the overall reaction. Now, this was proposed by Hess, so this is known as Hess's law. Hess's law simply states that a chemical reaction is a state function, meaning no matter which pathway a reaction takes, the overall change in enthalpy is the same. So a reaction may have multiple steps with multiple activation energies, but at the end of the day, all that matters is the change in enthalpy between your reactants and products. So the heat of the reaction is simply that overall change. It doesn't really matter how many steps there are involved. In the end, the change in enthalpy for the reaction is going to be a state function. So when we have to determine the enthalpy of a reaction using Hess's law, you'll be given a number of equations, and you have to order them in such a way that you end up with the overall reaction that the problem is looking for. So overall, when everything is said and done, I need to end up with this reaction. Now, I can order these in any way that I like. And however I change them, that's going to affect the enthalpy of them, right? So if I double a reaction, if I need 2 of reaction A, I would end up with twice that enthalpy. Or if I flip reaction A, right? If I take the inverse of reaction A, then the sign of my enthalpy inverses. Personally, I enjoy doing Hess's law problems. It's kind of like Sudoku for chemistry. In the end, there is one methodology, there is one answer that logically will give me the ending reaction I'm looking for. Different people tackle Hess's law problems differently. Personally, I try to get everybody in the place I need and trust that the equations I'm given will land me at my answer. So what do I mean by that? Well, let's watch as I do. So I'm going to label my reactions so that you can easily see what I'm using and what happens to it. So the first thing I'm going to do is I'm going to look at this first player, the first species, boric acid. I need 2 boric acids. Now boric acid only is seen in equation A. So I need to take equation A, and I'm going to need to double it because I need 2 boric acids in order for my equations to even start. So I'm going to double equation A. I keep track of those delta H's off to the side because when everything is said and done, I'm going to add them all up to get the heat of the reaction. By doubling equation A, I have the 2 boric acids I need. So boron oxide is my next thing I need. Boron oxide only appears in equation C. But there are 2 boron oxides in equation C. So I don't need all of equation C, I only need half of equation C. So I'll simply add that to my list of reactions. Now, water appears all over the place. So that I know that I have water as a product. I don't have enough, right? If you look at our products right now, we have 2.5 waters, which is not enough. I also have a bunch of other things here that I don't particularly need. I do not need this compound or this one in my reaction. So I need to get rid of them by putting them on opposite sides of the equation. Let's tackle this first one and hope that the second one gets handled. So H2B4O7 appears in reaction B. So I need reaction B, but I need it so that H2B4O7 is a product. So I'm going to take reaction B and I'm going to flip it. I'm going to flip reaction B so that H2B4O7 is a product, and I need to get rid of half of it. So I'm going to take half of reaction B's inverse. So writing reaction B out, I get 2 HbO2s produce half an H2B4O7 plus a half of water. Now again, everything I did to reaction B, I need to do to the enthalpy of reaction B. So that negative 11.3, I'm going to take half of, and since I flipped reaction B, the enthalpy flips as well. So this is a positive 11.3. Now, before we add everything up, we need to double check. Is everybody here that needs to be here? Yes, I know that boric acid and diboron trioxide is present. However, what about the other players? Did they cancel out? Well, this species, 2 of them appear on both sides, so they must cancel out. And same with H2B4O7. They cancel out. A half cancels a half. These are examples of intermediaries. Why? Because they are produced and then later consumed. If they were catalysts, they would be a reactant and then later a product. But since they are gone, the overall reaction hopefully matches what the question was looking for. I end up with boric acid and diboron trioxide, and 2 plus a half and a half is 3 waters, which is what I was looking for. So, since all of that matched, all of that works, I can add my enthalpies to give me a enthalpy change for this reaction of 14.36 kilojoules for each mole. For this next one, why don't you pause the video and try exercise 7 by yourself. In just a moment, I will speed through the answer. Hopefully you were able to land that you take B as is, inverse C and half it and half A in order to end up with an overall reaction that matches the problem given. And therefore can determine that the enthalpy for this reaction is a negative 3,237 kilojoules for each mole of reaction. With that being said, you are able to do page 16 in your packet. Lastly, we can calculate enthalpy if we think of chemical reactions as simply a rearrangement of the atoms themselves. In order for our reactants to form products, our reactants have to break apart from one another. Every atom has to be freed from its chemical bonds, and then they rearrange and come back together to form your products. The forming of products releases energy because compounds form bonds to reach a lower energy state, while breaking bonds requires energy. Think of it like Legos. If you want to take your Millennium Falcon model Legos and turn it into a Death Star, you have to break all those pieces apart. That's going to require some effort on your part. You're going to have to separate them, pull them apart. Breaking bonds takes energy. But when they come together, they just snap right in place. They release that energy. So coming back together releases it. All this means is that you'll be given the bond energy for your reactants and products, and you simply have to assign them positive or negative values. Your reactants are going to break apart. That is going to require energy. Your products are going to form. They're going to release energy. So when reactants break apart, we are going to assign them a positive value, and when products form, we'll give them a negative value. Personally, if I'm dealing with a very simple reaction, like this one here, I would classify as fairly simple. I like to write it and draw it out just so I can visualize it, especially when I was first learning it. So for hydrogen, hydrogen is a single bond, and fluorine is a single bond. Now they break apart and reform into two hydrofluoric acids. Now each of those breaking and forming have some energy assigned to them. When the hydrogen-hydrogen bond breaks, it's going to require 432 kilojoules. And when fluorine and fluorine bond breaks, it's going to require 154. However, each of these hydrofluoric bonds are going to release 565 kilojoules. In order to determine the enthalpy of this reaction, I simply add up all the values on the page. So, 432 plus 154 plus a negative 556 twice, to give me an enthalpy of this reaction of a negative 544 kilojoules for each mole of reaction. So with that being said, on page 17, I've done you a bit of a favor. I drew the Lewis structures for all 5 problems. Use the Lewis structures and the average bond energies for the particular bonds and determine the enthalpy of each reaction. And with that, we are done with Unit 6.2. I will see you when we wrap all of this up in 6.3.